Welcome back to another explainer. I'm absolutely thrilled you're here today because, well, we're going on a seriously fascinating, highly structured journey. We're going to span thousands of years of language evolution, starting with the bizarre quirks of ancient grammar and ending up right at the cutting edge of modern computer science. It's a massive timeline, but I promise you, by the end of this, you'll see the exact thread tying it all together. So to kick things off, let me throw a bit of a curveball your way. What could a shrewdness of apes and a battery of barracudas possibly have in common with machine learning? Kind of wild, right? And while you're mulling that over, get this. A cackle of hyenas sounds like a group having a good laugh, but it actually expresses anger, frustration, and a warning to stay away, not amusement at all. Human language is completely wild, but believe it or not, it all boils down to one essential element. The answer? The foundation of language itself, the noun. That's right. That basic building block we all learned about way back in grade school is exactly what connects our messy, colorful human quirks to the highly structured, rigorous world of computer science. Nouns are literally how we categorize the world around us, and as you'll see, they're exactly how we're desperately trying to teach machines to understand us today. To get us from a shrewdness of apes all the way to natural language processing, here's our roadmap. First, quirks of the noun. Second, grammatical gender's ancient origins. Third, the unstructured data problem. Fourth, teaching machines to extract. And finally, co-reference and future challenges. Okay, let's dive right into section 1, quirks of the noun, and look at human categorization. Let's break down these basic types. First step, we've got proper nouns, which name a specific person, place, or thing, like John or London. Then we have common nouns, naming a general type of thing, like girl or city. Now, I want you to really lock these categories into your memory right now. They might seem incredibly basic, but they're absolutely crucial for when we look at how computers actually attempt to read human text a bit later on. But of course, human language doesn't stop at just physical objects, and this is where it gets incredibly tricky for computers. We also use abstract nouns. These are invisible ideas with no physical existence whatsoever, like love, justice, or time. And then we've got gerunds, which are literally physical actions, verbs, that we've just decided to dress up and use as noun building blocks. Like the word running in the sentence, running is good for you. We humans, we process these shifts effortlessly. But for a machine, trying to turn an invisible concept or a literal action into a solid thing is a massive computational headache. Moving right along to section 2, grammatical gender's ancient origins. If we look back thousands of years to the oldest attested Indo-European languages, specifically the Anatolian branch, linguists note something really interesting. They only had a two-way distinction. Nouns were basically either animate or inanimate. It was only later, likely around the mid-4000s BC, when the Anatolian branch split off, that the system shifted into the three-way grammatical gender distinction we see in so many languages today: masculine, feminine, and neuter. Now, a lot of people understandably get tripped up by the term gender in grammar, but let's deconstruct that word neutrally. As this quote highlights, the linguistic term gender originally just meant kind or type. It actually comes from Latin roots related to genus or genre. Ancient Roman grammarians like Varro tied it to the verb genero, which meant to beget or breed. So it was really just a classification system for words, not necessarily a reflection of biology. The association with biological sex came shortly after, but it definitely wasn't the original rigid foundation of the concept. Because grammatical gender was fundamentally a property of the word itself and not the biological reality of the thing it referred to, ancient languages were full of these fascinating mismatches. Just look at this. In Greek, diminutives were neuter. So pagion, meaning child, was grammatically neuter, completely regardless of the child's actual sex. In Latin, homo, meaning human, was always grammatically masculine, while persona, meaning person, was completely fixed as grammatically feminine. Basically, we humans built a wildly complex, exception-filled system to categorize our nouns, which brings us to section 3, the unstructured data problem. Fast forward to today, and we're facing an absolute explosion of information. News articles, corporate emails, medical records, blogs, social media posts. We are generating mountains of data every single second. And the vast majority of this is what data scientists call unstructured free text. Now, this flowing, nuanced language is absolutely beautiful and totally natural for us humans, but it is an absolute nightmare for machines. Computers thrive on structured tables and spreadsheets, not the chaotic, exception-filled grammar rules we just looked at. So processing this information overload requires a serious bridge between human language and machine logic. Let's see how we build that bridge in Section 4, Teaching Machines to Extract. To build this bridge, computers rely on a general information extraction architecture pipeline. This step-by-step process brilliantly illustrates how computers attempt to turn our raw, messy strings of text into structured, highly usable data. You can see how it flows from raw text down through sentence segmentation, tokenization, all the way to extracting actual relationships and events. Let's actually break down what's happening inside these boxes. A machine basically has to carefully dissect a sentence, piece by grammatical piece. Step 1 is tokenization. This is where the machine slices the text up to extract individual tokens or words. Step 2 is part of speech tagging. Sound familiar? This is where the machine acts like an automated grammar teacher, assigning labels like verb, adjective, and importantly noun to each token based on its context. And finally, we reach Step 3, named entity recognition. So, what does named entity recognition actually do? Well, it hunts down categories like person, organization, location, and geopolitical entities. If you think back to our very first section, NER algorithms are literally hunting down the exact same proper and common nouns we defined earlier. By teaching a machine to find the specific Johns and Londons hidden inside a chaotic paragraph, we can begin to convert human sentences into structured databases. And that leads us into our final section. Section 5, Co-reference and Future Challenges. You know, we humans love our shortcuts. Instead of repeating specific nouns over and over again, we just use pronouns. We'll say, I have seen the annual report. It shows that we gained profit. But for machine, that word it is a total dead end. Unless, that is, we use something called co-reference resolution. This is how we teach machines to connect the dots and figure out that the vague pronoun it points directly back to the specific noun phrase annual report. This step is absolutely vital for natural language understanding and text summarization. Once a machine can finally identify the nouns and resolve those tricky pronouns, it can do something pretty incredible: relation extraction. This involves pulling actionable facts and structured relationships straight out of unstructured sentences. For instance, if a machine reads Jodie Foster is an American actress who won an Academy Award, relation extraction turns that into a structured data tuple, one Jodie Foster Academy Award. This exact process is what powers the question-answering systems you probably use every single day, like the digital assistants on your phone. They search through these extracted facts to give you direct, accurate answers. But despite all these incredible advances, NLP still has some massive hurdles to overcome. Future frontiers include OpenIE, which tries to extract unrestricted relations across the entire web without any predefined categories. Then there's BioIE, which really struggles with processing highly complex, abbreviated medical and patient discharge texts. And perhaps the most difficult challenge of all, teaching machines to separate concrete facts from shifting opinions and misinformation online. Which leaves us with this final, really provocative question to ponder. As digital data continues to explode exponentially, how will machines master the constantly shifting chaos of human facts, opinions, and misinformation? We've come a very long way from ancient Roman scholars debating the gender of nouns to algorithms parsing billions of web pages. But language, with all its beautiful human messiness, definitely remains the ultimate puzzle. Thank you so much for joining me on this explainer. Keep learning, keep questioning, and I'll catch you next time.